Here we have a trough where the two ends are in the shape of trapezoids, and the trough is the length of it is 10 feet, and then 9 feet across the top here, and then the bottom here is 5 feet. And so the ends of the trough, the trapezoids. And so we have water being pumped into the trough at a rate of 2 cubic feet per minute. And so as water is being pumped into the trough, the height of the water is rising. And so we'd like to know how fast is the water level rising. And so right now we're at a height of about 2 feet. And so the distance from here to here is 2.2 feet. And when the height of the height of the waters is about 2.2 feet, then the corresponding volume of the water inside the trough is about 148.72 cubic feet. And then if we go higher, and right now we're at a height of about 3 feet, and the corresponding volume of water is 222 cubic feet of water. And right now we're at a height of about 3.6 feet. The water level is at a height of 3.6 feet, and the corresponding volume of water is 283.68 cubic feet. And so the question we have is, if water is being pumped into the trough at a rate of 2 cubic feet per minute, how fast is the level of the water rising? And so let's call this H. And so we call this H, and we like to know how fast is H changing. And so we like to find dH dt. And so let's find dH dt. And so we're calling the height of the water, or the water level right here, we call this H. And recall that across here, this is 9, and this is 5, and therefore that makes this one 2, and that makes this one 5. So the distance from here to here is 2, and the distance from here to here is 5. And the water, let's call it the distance from at the bottom of the trough to up to the water level right here. Let's call this H. And then call this distance right here X. And so this right triangle right here, this distance is 2, and then from here to here is 5. And then across here we have X, and then from here to here we have H. And so this smaller right triangle is inside this larger right triangle. And so these two triangles, they are similar. And because they are similar triangles, what that means is this: the ratio of X over H would be the same as the ratio of 2 over 5. So X over H would be the same as 2 over 5, because the two right triangles are similar. And so let H sub W, that be the height of the water, since we have the height of the trough, and then we have the height of the water. And so we'll let HW be the height of the water. So it means that X over HW be 2 over 5. And then cross multiply, we have X times 5, which is 5X. And then 2 times HW sub W is 2H sub W. And then dividing both sides by 5, then we get X equal to 2/5 HW. And so for the water, this is the trapezoid. for the water. And to get the volume of the water, we have to find the trapezoid of the water and multiply it by the length of the trough. Area of a trapezoid is 1/2 times base 1 plus base 2 times the height. And we want this trapezoid, water trapezoid. And to get the volume of the water, we have to find the area of the water trapezoid here and then multiply by the length of the trough. And so in this case, base 1 of the water trapezoid here, base 1 is 5, and then base 2 will be x plus 5 plus x. So it will be 2x plus 5. And then the height of the water will be denoted as HW. And so the volume of the water will be 1/2 times base 1 plus base 2 times the height of the water, and then multiplying by the length of the trough. And so in this case we have 1/2, and then base 1 plus base 2 will be 5 plus 2x, will be 5 plus 2x plus 5, and then this is the height of the water, and then the length of the trough is 10. And so the length of the trough right here is 10. And then we're just combining some things here, a few things here. And so 1/2 times 10 will be 5, and then 5 plus 5 is 10, and so 10x. So we end up with 5 times 10 plus 2x times the height. 5 times 10 will be 50, 5 times 2 will be 10x. 50 times HW will be 50 HW, and then 10x times HW will be 10x HW. But earlier we found that x is 2/5 times HW, and so in the place of this x we have 2/5 HW. And so now the volume of the water would be 50 HW, 10 times 2/5 is 4, and then HW times HW is HW squared. And so this is the volume in terms of the height of the water. We're given that the water is being pumped into the trough at a rate of 2 cubic feet per minute. And so we like to know how fast is the water rising when h is 1.5 feet. And so right here, this is when the water level is at 1.5 feet. At that time, the volume of the water is 93 cubic feet. And so at this time, we like to know what is the rate of change of h, of the height, when the water level is when the height of the water is 1.5 feet. So that's what we're looking for. And so we're looking for the rate of change of the height of the water. And so what we'll do is we'll do implicit differentiation right here with respect to t. The time t. Since the volume changes with respect to time, and the height, which is the height of the water, also changes with respect to time. And so this is 1W, 1V, and so the derivative would be 1 times, and since we're doing derivative with respect to t, and there's no t here, therefore we have to use the chain rule, and we have to multiply by dv dt. And the derivative of 50h, so do the regular derivative, which is 50, and then this is h, and we're doing derivative with respect to t, and so we have to multiply by dh dt. And this will be 4, and the derivative of h squared is 2h, And again, we're doing derivative with respect to t, so we have to multiply this by dH dt. And so this becomes dV dt. That's the rate of change of the volume of the water. And then this is 50 times the rate of change of the height of the water. And this will be 8h times the rate of change of the height of the water. And so now we have the common factor here is dH dt. So let's go ahead and factor that out. And so what's left is 50 times 8h. And we'd like to know what is the rate of change of the height of the water. At the moment, the height is 1.5, or the height of the water is 1.5 feet. And we're given that water is being pumped at a rate of 2 cubic feet per minute. And so dV dt will be 2 cubic feet per minute. And then at the instant when h is 1.5 feet. And so h right here will be 1.5. And then we're looking for dH dt. We're looking for the rate of change of h with respect to time. And so this is our equation right here. And the rate of change of the volume of water is 2. And then h is 1.5. And then to solve for dH dt, it'll be 2 divided by all of this. And it'll come out to be 0.032258. And therefore, the water level is rising at a rate of 0.032258 foot per minute. And then we have a second question. The water level is rising at a rate of 1/2 inch per minute when the height is 2 feet. And so right now the height of the water is at 2 feet. What is the rate at which water is being pumped into the trough? So water level is rising at a rate of 1/2 inch per minute. That will be the dH dt. It would be 1/2. And then when the depth when h is 2, what is the rate at which the water is being pumped into the trough? So we're looking for dV dt. That's what we're looking for. So the h right here will be 2, and then dH dt will be the 1/2. Let's back up for a few minutes. Now the rate of change of the height is given as 1/2 inch per minute, but recall that our unit is in foot per minute, and therefore we need to change the 1/2 inch per minute to foot per minute. So 1/2 inch per minute is to convert it to a foot per minute, and then we multiply by 1 foot divided by 12 inches, because 1 foot and 12 inches are the same. And so 1/2 times 1/12, it'd be 124. And then now we get foot per minute. And so the volume, the rate of change of the volume now would be 50 plus 8 times 2, because that's what the height is. The height is 2 feet. And then the rate of change of the height of the water in foot per minute is 124. And then multiply all this out, we get 2.75 cubic feet per minute. And so in summary, if the water level is rising at a rate of 1/2 inch per minute, and then when the depth of the water, when the height of the water is at 2 feet, then the rate of change of the volume is 2.75 cubic feet per minute. And that's how fast water is being pumped into the trough.